All right, Foundations of Math 24.2. We're talking today about proving and applying sine and cosine laws for obtuse triangles. So obtuse triangles are triangles that have at least one what? Or only one, you can't have more than one of these, but have an angle that is what? Yeah, between 90 and 180. So it's got an obtuse angle. An obtuse triangle is a triangle that has one obtuse angle. Again, you can't have more than one obtuse angle in a triangle, right? If you think about that, you could not draw that, because if this is obtuse and then the other one's obtuse, there's no way that those would meet anywhere. So you can only have one obtuse angle in a triangle. So we've talked about sine law and cosine law for acute triangles. So let's explore what happens with obtuse. See if there's any differences at all. And there is one slight difference. Now, I'm not going to spend too much time going through the proof of the sine law for an obtuse triangle, but I do want you to watch carefully as I just go through it. So if we have a triangle ABC that is obtuse, so you can see that this angle is greater than 90, the height of the triangle, if this obtuse angle was one of the base angles, the height is outside of the triangle, okay? From the top to the base there, if the base was BC. So the height is outside the triangle. So let's try and build a sine law the same way that we did with an acute triangle. Remember the acute triangle? What we did was we had an acute triangle and we drew a height inside. Remember that? So this one is a height outside. So see how that changes. Well, sine of C is equal to the opposite side, which is the height. It happens to be outside the triangle, over the hypotenuse, which is B. So sine C is still H over B. Okay? Also, if we were to do this a different way, or to rearrange this, H is B sine C, okay? Now, over here is where this gets a little tricky, okay? The sine of, now we know about, okay, now, what we're focusing on here, sorry, is right here, this angle, okay? So this is the sine of 180 minus B. So we're focusing on this little angle right here. So the sine of 180 minus B is H over C. You see that? Because we are actually looking at this little right triangle in here, that right triangle. So if you take a look at this one, that's the supplementary angle to B, isn't it? That's the supplementary angle to B. And so I can rearrange this statement to be H equals C times sine of 180 minus B. And if you notice carefully, the sine of 180 minus B and the sine of B are the exact same. Okay? So I wouldn't expect you to be able to do this on your own right now, okay? But again, the large triangle that we did first was this one, with angle C, and the smaller triangle that we looked at secondly has angle 180 minus B right here. So that's 180 minus B. Now, because these are the same, then what happens is we get the same equation that we got when we were proving the sine law for an acute triangle, which means that even for obtuse triangles, the sine law still holds true. Okay, so that was just a brief little explanation of how we got that. We capitalize on the fact that the sine of an angle and the sine of its complement, the complement being an obtuse angle, are the same. So the sine law is exactly the same even for an obtuse triangle. So please write this down. The sine law holds true for obtuse angles, or for obtuse triangles as well. There's one catch though. And this is what I want to talk about here. There's one catch. The only catch in using the sine law for obtuse triangles is this. When you find the angle associated with the sine ratio, your calculator will always give you an acute angle. So let me just explain this. Let me just demonstrate this for you, I guess. Demonstrate. So if I say, okay, so the sine of 140, similar to the example we did, the sine of 140 is this value, right? Okay. Now, if I got this value in my calculations with the sine law, and I said, okay, I'm going to find the angle. The second function sine of the answer, that is the 0.6427876097, look at what the calculator gives me. It gives me 40. Now, why didn't it give me 140? It always gives you the acute. Why? Why does it do that? More common to deal with? Okay. The calculator doesn't know when you give it this value, because the complement is the same value, it doesn't know which one you're actually looking for. So by default, the calculator will always yield you a first quadrant angle. And then it's up to you to decide, is that going to be the angle that you're looking for in the question? Or do you need, for the sine value, do you need the supplementary angle? Okay? So that's why you kind of have to know, like you should sketch your triangles when you're trying to find an angle. You should try to sketch and try and sketch to scale a little bit so that you can see if that one angle is acute or if it's obtuse. Because you're going to have to do that extra little calculation on your own. The question's not always going to tell you to do that. So it'll always give you an acute angle. This means that you have to look to the triangle to observe if the angle is acute or obtuse. That's up to you to give your final answer. The calculator will not know which angle you're looking for. So let me do an example, and I will do an example exactly of this. I would appreciate if you write this down as that example, and I will show you exactly what that looks like. Okay. So we have triangle ABC. Angle B is 23. And side A is 65, side B is 40. And the triangle here is drawn for you, and can you see that angle A is obtuse? Okay, so angle A is definitely obtuse here. Awesome. So this is we can use the sine law, but we're going to have to do one little extra calculation at the end because this is obtuse. So the sine law states that I would take the side length and its opposite angle pair. I need to use those as my base. So I'm going to do sine 23 over 40.0 equals sine of A over 65.0. Okay, so please let me know if you have any difficulty understanding why I set this up this way. Is there any problem with that? Yeah?
Isn't the sine of 23 always on the bottom?
Okay, thank you for asking that. Isn't the sine of 23 always on the bottom? Well, yeah, you look back here and say, hey, Mr. Maxwell, look at this. The sine is on the bottom for what you just told me. So what you want to remember from last chapter when we first learned this, that you can have B over sine B, A over sine A with on the bottom, or you could have the reciprocal as well, as long as you change everything over. If everything changes over, then it works to have the angle on top. Okay, so yeah, that looks a little different. Now, why did I set it up that way? Can anyone see or remember from last section? Yeah, because I'm looking for the angle. So why is that important? Well, that's going to save me one little calculation. Okay, if I don't have to bring this sine A from the bottom all the way up to the top, that saves me one calculation. So it technically is a little bit easier if I put my missing value on the top somewhere. Okay, so that's why I did that. Because look, all I have to do now is multiply both sides by 65.0, and now I've got my sine A value. So let's do that. Let's do 65 times sine of 23 degrees. Make sure you bracketed that, and then you can do all this in once, divided by 40, and I get 0.63493. 0.63493. Now that equals sine A, doesn't it? And so, in order to get the A value, I need to take the sine to the -1 of both sides. That will get rid of the sine on the right. And second function sine of the answer. Use your answer function so it copies all the decimals for you. And you get 39.4. Okay, so A It's telling me it's 39.4. So this is what I'm talking about. The calculator will always give you an acute angle. It's up to you to use your brain and say, oh, you know what? What I need is an obtuse angle. So guess what? Angle A is actually 180 minus 39.4 degrees. That make sense? So that's 140.6. That's very similar to the earlier example we did. Now your textbook will probably round these up to 40 and round this down to 140, okay? So that's probably what your textbook will do. I appreciate a 1 decimal place. I like that a bit better, just because it's more precise. It's not hard to do, and it's far more precise. So I appreciate 1/10 of a decimal when you can, but either or is fine right now. Okay, so I reject this answer, the acute one, and I favor this obtuse angle there. Does that make sense? Okay, all right. So with obtuse angles, you can use the sine law, no problem. You just have to do 180 minus the answer you get if you're looking for an angle. The side length should be no problem. The side length, no problem at all. Because guess what? If I was given 140.6, watch this. If I did 140.6 here, and I didn't know what, let's say, I didn't know what one of these values were, 23, 40. I didn't know what the 65 was, okay? If this was the question, this was x, I could solve for x, and sine of 140.6 just gives me this value right here. It's like, no problem. You don't have to change anything around. You'll get the right length. So you don't have to do anything with the length. You just have to do 180 minus the angle, okay? All right? Okay, hopefully you got that. Let me go back and not mess up this question here. Okay, come on, backspace, undo. Yeah, come on. All right. Okay, one more example. The question is there a similar catch, or is there something we have to do when we do the cosine law? That's the question. So, is there a catch? Do you know what I mean by a catch? Yeah. It means like there's something you have to remember, like, so you don't get caught. Like missing something. Okay, is there a catch? That's a phrase, right? It's a figure of speech. Okay, what's the catch, right? If someone says, "Hey, I got $1 million for you. Here you go." What's the catch? Like, what do I have to do for that? Oh, you have to, go commit a crime for me, and you might go to jail for the rest of your life. But hey, that's the catch. You see? It's like, say no, kids. All right. Now here's the same type of triangle, right? But let's do one where this is a new one I want you to do. Here's the triangle, and this angle is obtuse, but I'm given an SSS situation, and I know that I have to use cosine law for that, right? Side, side, side. All right. So let's do this. Let's figure it out. Let's see if there's a catch with the cosine law. Okay. So who remembers how I set this up? If I want to find angle C, well, I know that cos C, I guess, should go to the back there, right? Okay. What goes on the very far left here? Which number?
33.5 squared.
Very good. 33.5, make sure you remember to square it. Good. The one that's opposite goes on the opposite side of the equation. In here, I'm going to make it look just like Pythagoras, so it's going to be 17 squared plus 20.3 squared, right? Looks just like Pythagoras. But then I have to do minus 2 times these numbers here. Yeah. Okay. Okay, so are you guys remembering this from last chapter? How to set this up? Okay, good. Good. So everything looks pretty cool. I wonder what's going to happen when I solve for C. So, okay, let's do this together. Let's run through this here real quick. Okay, little calculation here. This is what I get. I'm going to subtract 289 and subtract 412.09 from 1122. Let's see. 1122.25 minus 289 minus 412.09 equals 421.16 Okay? Divided by, and now I'm going to divide by this negative 690 number. Okay. So divided by negative 690.2 is, sorry?
Did you add 289 plus and you only
I subtracted the 289 and the 412 both from this number. So this 421, did everybody else get this 421?
Yeah.
Okay, you guys are my double checking my math here, so if you get a different number, let me know. I'll double check it. So look at this, negative 0.610199. So negative 0.61, okay, 0.610. Why can I not remember that? 1901,999. Okay, equals cos C. Now, here's what I want you to see with this. If you do everything correctly and you take care of your negative signs, and that just disappeared on me. 6101. If you take care of all your signs, notice this. You'll have a negative sign here. And when you take the second function of that answer, so let's do it. Second function cos of the exact answer, including the negative, see, negative 0.610199, I get, look at, it gives me my obtuse angle. Do you know why it does that? 127.6, so let's write that down first. So angle C is 127.6 degrees. Now the reason why you don't have to do a 180 minus trick is because the calculator knows that when you put a negative sign here and you're looking for a cosine of an angle, it knows that the angle has to be in the second quadrant. Well, actually it could be in other quadrants, but between 1 and 2 it has to be in 2. So it will always give you an obtuse angle there. So with the cosine law, you don't have to do, there's no catch. You don't have to do any little trick at the end, okay, to remember to minus this or whatever. The cosine law will always give you the right one. If it's a positive value, then it will give you an acute angle. But if it's a negative value, then it will give you an obtuse angle, and that's exactly what we're looking for, okay? So remember that cosine is negative here in the second quadrant. So by this negative number, the calculator knows you're looking for something that terminates in this quadrant. Question, yes?
Why is there a catch for the sine law then?
Well, there's a catch for the sine law because remember that the sine in both these quadrants are positive. Sine's positive and sine's positive here too. So your calculator, when you plug in 0.64 or whatever it is, it doesn't know whether you're looking for an acute angle or the obtuse angle. It doesn't know. So it always defaults to giving you this one.
Why is it negative in the second quadrant?
Well,
Or
cos,
positive? It's not negative. It's second quadrant.
yeah, sine is positive in the second quadrant. Okay, now I think I went over this with, did I go over this with you guys? With the so if, I don't know if no, this is not for this course. But anyways, anything that ends in this quadrant, like an angle that terminates in this quadrant, would have a point on the terminal arm in that quadrant. So how you can remember this is that the coordinate for this point on the terminal arm is a negative x value and a positive y value. Now what we did talk about, I'm pretty sure we did talk about in this class, was that the first coordinate of a quadrantal point, quadrantal angle, is, the first coordinate is the cosine, and the second coordinate is the sine. Well, that holds true for every angle, as long as that point is on the terminal arm of the angle. So if you think about what the values for this point would be, you would have a negative x value and a positive y. That means we have a negative cosine and a positive sine. We won't focus on that until next, like another class, pre-calculus, okay? We're going to focus on that in pre-calculus. But just so you know, there's lots of different reasons why, I guess, the sine is positive in the second. That's one of them. And again, I think because the sine of an acute angle and its supplement are always equal, that's another reason why the triangles work out like this. But yeah, so that's all I'll say about that. Okay, for now? All right, so here's your assignment 4.2. Write that down, and you can get started on that. Sine law, cosine law for obtuse triangles. Yeah.
We have six trig functions, right?
There are 6 trig functions, yeah.
Are we going to deal with the rest?
In this course, I don't think so. No. Sine, cos, tan, and cosine, secant, and cotangent. Yes, not this course, but later. You bet.